I think it means chances.
Okay, that's a good start. Anybody else?
The probability of
Your
winning
chance of
versus.
winning.
I'm not a gambler, but I think it means probability.
I love the disclaimer, by the way. Okay, so if you also chances or probability, so are you saying that chances or probability is the same thing as odds?
I think odds are a ratio of probability of success or failure.
Who is that person? Wells, do you want to come and teach the class? That was very spot on. So please, can you just repeat that again so that everybody gets it? What's the difference between odds and probability? And odds represent a ratio of what?
Okay. When we look at odds, normally we say it's an odds ratio, which means we have a numerator and a denominator. The numerator is the probability of success, then the denominator becomes the probability of failure. That makes it the odds ratio.
You are doing so well. You now just veered into the bush all of a sudden. What we're talking about is odds. We've not got into odds ratios yet, right?
Okay.
We're talking about just odds. So initially you said it so well, but now you moved from odds and you started defining odds ratios. For now, we're just talking because what you have here is odds, right? It said odds less than 1.25 and so on and so forth. So we're just focused on what are odds. If we don't know what odds are, we cannot understand what odds ratios are. So what are odds? And just go back to what you said initially. You said it so well done. I don't know why you veered into the bush all of a sudden. So what are odds, Wells? Sorry, I'm picking on you. You said it so well the first time.
Okay, I hope I'm gonna do that again. So odds, my understanding is that it's the probability of success divided by the probability of failure. That's my understanding of odds.
So in other words, odds is the ratio of two what?
Two probabilities.
Excellent. So you see, so that is exactly right? So odds represent the ratio of two probabilities, the probability of an event occurring and the probability of event not occurring, right? And so this is quite different from likelihood. So the first mistake you see people writing in research, they'll say they will fit a logistic regression model. And here is how they will interpret it. They will say results from our logistic regression analysis showed that males were 2 times more likely to smoke than females, right? Males were 2 times more likely to smoke than females. What is the problem with that sentence? Males were 2 times, based on results from from the logistic regression model. Males were 2 times more likely to smoke than females. What's the problem with that? Which word is the problem word in that sentence? Yes, Johnson.
Likely.
Likely.
Excellent. All right, likely. And here's why it's a problem. Like we said, odds is the ratio of two probabilities. The probability that the event occurs over the probability that the event does not occur. And now word for probability is likelihood, right? Likelihood over on the top divided by likelihood over the bottom. What happens? If you have likelihood on top and likelihood at the bottom, what does it do in terms of canceling each other out? They cancel each other out, right? So that means that with odds, you cannot have likelihood because you have likelihood at the top and likelihood at the bottom, and those two cancel each other out. So that's the error number one we want to avoid, right? Please, if you're using odds ratios or logistic regression, please don't let me catch you saying the word likely or likelihood, right? Because it does not make sense. We're saying an odds is the ratio of two probabilities or two likelihoods. The likelihood that the event occurs over the likelihood that the event does not occur. And so you can see just from this formula why it does not make any sense to use the word likelihood in the context of odds ratios because they cancel each other out. And so odds means odds, probability means probability. They're not the same thing. Now, logistic regression is used for binary outcomes, dead or alive, smoker or non-smoker, or any of those other examples on the page, right? Now, that does not mean that the variables were captured as binary. Sometimes the variables are captured in the form that is non-binary, but we just collapse them to binary. So for example, this is a question that says, have you smoked at least 100 cigarettes in your entire life? The response options are yes, no, don't know or not sure, or refuse. So there are 4 categories here, right? What do we do with responses? Imagine we wanted to analyze this variable as binary. What do we do with those people who answered don't know or refused? Because remember we said earlier in the previous screen that we use logistic regression for binary logistic regression for outcomes that are binary. So here, the argument is that you obviously should not expect that the variables will be binary in nature or in how they were measured. Sometimes we have to encode them to a form that is binary. And the example is this. This is 4 categories. We want to collapse it with 2. So this is a question. So when answering this question, remember the 3 types of biases that exist, right? And pay special attention to measurement bias. How should we deal with the case of don't know or refused? How do we categorize them? What will you do?
I think I'll categorize them as negative, as one category. Then those ones that outrightly know will be yes. The other 3 categories will be no.
Okay, so you are saying that you're going to group people who said don't know with those who said no.
Yes.
What's the problem with that approach? You are making an assumption, right? And what's the assumption you're making there?
Well, the assumption is that those that say they don't know, probably those that say no, they don't know, I cannot outrightly say they know. So assume that if you know, you know. So any other thing less than being that you know means you don't really know.
Okay, that is a fair answer, but it is not an acceptable answer in this secret gathering. Yeah, who has a different opinion?
I'd like to think that.
Hello.
I would like to think that if someone declines, it is because he does smoke, but does not want to admit. So I could lump them with those who would normally say yes, or on the extreme, I could clean out the data and take them off the take the response off the data. I mean, the data collected.
Yeah. So again, you're making an explicit assumption here, right? You are just assuming that if the guy says I don't know, that means that they smoke and they're just trying to deny that they don't smoke. So once again, with the previous answer, we have assumptions creeping into the data, right? Our personal opinions of what we think somebody answered creeping in. Does anybody have any other opinion? Abubakar.
Okay, I think I have. Okay, go ahead.
Yeah. So for me, those responses will be dropped in the data, and then I'll use the yes and no for them. So in that case, the sample size.
Doctor, let me try again.
Please go ahead.
Since it is not a certainty, I would assume it is 50% yes, 50% no.
Exactly. So since you cannot identify those who are 50% yes or 50% no, what then do you do with that?
Hello. I think that I would have to code each of the answers as in don't know, I'll give it yes or no. So those who choose the don't know, I'll give yes. Then those who do not choose, I would also code it no, since we are dealing with binary variables. So each of the responses would have to be analyzed individually.
Okay, that is a fair trial.
Okay.
Let's take
my opinion.
Let's go ahead.
I will randomly assign them to smokers and non-smokers.
Okay. Okay, those are all fair. Okay, well, we'll take one last response. Charles,
Yes.
So
Hello, sir.
for me, okay.
Okay. For me, I also want to do if an assumption. I'll also take the part that perhaps
because there's a specific question, like if they have smoked up to 100, if they have smoked up to 100 sticks of cigarette, perhaps the person have smoked, which they have agreed for you to have answered that question. You've agreed that you smoke, but perhaps you don't know if they have smoked up to 100 sticks. Just that would be my thing that will be running through my head.
Okay.
But
all right. So
they are smokers, yes, but they may not know the actual number they smoke, number of sticks.
okay. So there are two options you can do here. One, you can categorize those into a separate category as indeterminate answers. But now you have three categories, right? And so that will not fit in with the binary logistic regression. Remember, our topic for today is binary logistic regression. And so if we're looking at another type of regression, which is like multinomial regression, which allows for 3 or more categories, that will be fine. Yeah. Our focus today is binary. Binary means 2. So what we do typically in large surveys like this is that we are going to drop those values. 7 and 9 will be missing values, right? And so because there are 2 problems we are facing. One is the issue of if we turn them into missing values, we have less people in our sample. So we have the issue of precision, lowered precision by dropping them. But the other problem is the issue of misclassification bias. Imagine somebody is a smoker, that will turn them into non-smokers because we think. Now, the first rule of analysis is do not assume. No assumptions, right? So the 2 problems, we drop these individuals and we have less precision because we have a smaller sample size, or the issue of bias, misclassification bias. Well, between those 2, the issue of precision is a smaller problem. So it's better to drop those individuals so that we just manage the issue of precision and therefore. So those are some of the things that you have to consider when you are classifying or recording your variables to make sure that you achieve a binary outcome. And we'll talk more about this when we do a hands-on demo.
Sorry, can you say that again? I missed the last 2 lines. Your last 2 lines, please.
Okay, I said that the best approach is to recode them to missing values, because the issue of lowered precision with wider confidence intervals is less of a problem than the issue of validity. Because when we misclassify, when you make your assumptions filter into the data, you are now injecting bias into the study. In this case, misclassification bias. Because how do you know somebody says, I don't know? You are concluding that don't know means you must be a smoker and you're just hiding it. But it could be that, well, they are not in the mood to answer a question at that point, or whatever, right? So we can't assume. And so the best way to treat that is to set to missing values. And then that way, you know that you have a smaller issue to worry about, because the classification indeed could be non-differential. All right.
Thank you. Please, a little clarification again, please. If you are using a Likert scale, strongly agree, neutral, disagree, and strongly no, disagree, and you want a binary outcome from that, you drop anything or you just reclassify?
You reclassify, you recode. So don't just go around dropping values, right? The Likert scale you mentioned, that's a very different thing, right? And so in that case, you can analyze them the way they are naturally with a, I will discuss other kinds of regression in the next few weeks. This focus here now is on binary logistic regression. So in that case, you can recode into binary, but there are better ways to analyze that, which we'll discuss in next future sessions. Again, focus of this session is on binary logistic regression. All right, let's move on. So let's talk about regression coefficients. For us to understand to interpret regressions, we must understand what coefficients are. Coefficients are numbers that allow us to interpret whatever the output of our regression says. Think of them as the tag you see on a sales, like 40% off. 40% off, that tells us that, okay, whatever the price was, we're going to take 40% off that price. So these things are very intuitive to us. And so you should think of regression coefficients in that same light. Now, just as a warning, we also must make sure we understand the difference between causal inference and causal inferences, right? Those are very different. Causal inferences has to do with fitting regression models with with the intent to make causal inferences, to say that A causes B. Casual inference is all about saying A is associated with B. Everybody knows that association does not mean causation, right? So in the future sessions, we've had past sessions where we talked about methods for causal inferences. The way we fit regression models for causal inferences are very different. So we want to keep in mind that everything we're discussing today has to do with casual inferences or simply associations. And the way we interpret causal models is also very different from the way we interpret associational models. In causal models, we make use of counterfactuals. So we say, if the whole population was exposed compared to if the whole population was not exposed. That's how we think of causal models. In associational models, we're just looking at those who were exposed versus those who were not exposed. So keep that in mind. And again, we're going to have a future session on how to fit causal inferences or causal models and how to interpret them. But everything we talk today will be in the context of associations, meaning comparing this group versus that group, right? And we're not talking about any counterfactual scenarios. All right, now let's talk about hands-on now. So we have two groups here, males versus females. So what are the odds of smoking among males? That is Samira, please, can you mute yourself? So the outcome odds among males is 1/3. The outcome odds among females are 2/3. The odds ratios among males compared to females is the odds among males divided by the odds among females. This is 1/3. Well, of course, when you want to convert a divide into a times, we invert it. So 1/3 times 3/2, and that gives us half, right? So that is how we will calculate odds ratio. Now, in this case, this is very simple. We only have two groups we're comparing. There are no other variables in play. And so we can just take our paper and pencil and actually calculate the odds ratios. So the proverb, I don't even know where this proverb is from. It says it's easy to pick up one grain, but it takes effort to harvest the whole field. In the same way, it's quite different when we are looking at this kind of very simple scenario where we just have males and females versus in a more complex scenario where we have so many other variables we have to adjust for, right? This is like that case where we looked at just males versus females. And we can just take the odds in males and divide by the odds in females and just get a clean, nice number. In the real world, it's never that simple. You have a whole million variables you have to adjust for in your analysis. So obviously, we can't calculate odds ratios by just calculating the odds in the males versus the odds in the females, because what we're just getting here is just the crude odds ratios. So the question then is, if we wanted to calculate the odds ratios in the context of many, many other variables being adjusted for, how then do we do that? Well, that is where we now have to understand other concepts like, the odds and odds ratios and how they're related. This is the man who explains to us how we should go about this. Archimedes. This is the father of flotation, and if you remember your basic physics. If you remember, again, if your physics, he's attributed to the Eureka moment. One of the things that Archimedes taught us was that the shortest distance between 2 points is a straight line. In other words, and that sounds so simple, but it's quite revolutionary, because a straight line is the simplest way to explain any kind of observation or any relationship, right? So when we are faced with complexity in measurements, like this kind of complexity on the right-hand side, we just go back to a straight line and say, how do we use what we know about straight lines to measure relationships when we have so many variables, all right? So, and that is, in other words, we're saying we are going to go back to linear regression. And that's why the linear regression is like the root. Every kind of regression always seeks to default back to a linear regression to explain relationships. Why? Because a line is the simplest relationship between two phenomena, right? As Archimedes clearly stated, like when you have a complex relationship, a line just simply explains them in a way that is just elegant and simple for everybody to follow. So don't be wondering or don't be confused when the explanation for any kind of regression, most regression seems to default back to a linear regression. And that is because it is just a simple way to explain any relationship. So think of linear, think of lineage, right? All regression models owe their existence to a linear model, because when we have an unadjusted relationship, like we saw earlier, it is quite simple to calculate odds ratios. We simply take the odds among males, divide by the odds among females. But when we now have many variables in the mix, we can't do that anymore. And so we need to default back to a linear model because it is the simplest way to explain anything. Now, let's talk about why do we say that a linear model is a simple way to explain anything. To understand that, we have to understand why we fit regression models. So last week, we talked about the picture of an apple, and we said an apple is a model, right? Now, between these two models, which do you think is more complex, and which do you think is less complex? Which is simple, which is complex? What are your thoughts?
The overfit is
Overfit is complex.
Why is it
And then
complex?
The overfit is complex.
Okay. If you
And
want to
the generalized model,
okay,
the generalized model is simple.
Why do we call it overfit?
The overfit is damaged, and you have worm in it.
But why do we call it overfit?
Yes. Can I speak to that?
Please go ahead.
Yeah, thank you. So I believe it is overfit because in the first place, hello?
Yes, go ahead.
Yeah, it is overfit in the first place because there is a piece, you can see there is a piece of the apple that is being, cut off. And then you also see another stem that is, coming off. Unlike the one on the left, you see that it is plain, and one can see that it is beautiful and a clear look of an apple, unlike the other one.
Thank you very much. From our lecture last week, why do we need models? From those who were here last week, why do we need a model?
When we don't have enough data.
We want to have the data.
Yeah.
Excellent. And so why do we need a model?
So
you've answered,
to simulate the reality.
Exactly. So that we can do what? Like, for who are we trying to simplify reality for?
For those who don't know what the details are.
Exactly. For a guy who has never seen an apple, right? We need a model, a picture of an apple to tell him, hey, guy, this is what an apple looks like. So that this guy's like, oh, I see. Now, the problem is that this guy, if you're an artist, if you're the one who is now drawing the sketch of an apple, and the apple you are drawing looks like this, what are you supposed to do? If again, remember that the purpose of an apple is to just provide a simple, generalizable reality. It's a simplified version of reality for people who don't know what an apple is. If we present this image to somebody who has never seen an apple, what do you think might arise? What problems do you think can emerge from that depiction?
They will think that all apples are meant to have worms in them.
Excellent, right? So the worm and the bite, what do we call that? That's noise. It's just noise. It's an artifact of a data that it might be present in your data set, but it's not generalizable to all nature, right? It's an aberration, right? A model is supposed to exclude noise. And just so this is an overfit model because you are doing too much. You are capturing things that are not inherent in nature, right? And so you have failed the very premise for which we fit models, which is that it should simplify reality. Now, I present this slide to show you what happens when we do not default our regression models to a linear model, and when we are trying to do too much in our models. One of the things we learn on is that we try to achieve parsimony in our regression models. Parsimony means that we don't want to have too many variables. when you have too many variables, you will end up capturing relationships or depicting a picture of reality that may be true in your data set, but does not necessarily exist in reality. So you end up with an overfit model. If you end up trying to fit a regression model that does not default to a linear model, you end up with an overfit model as well, right? So again, keep in mind that we always default back to a linear model because it's the simplest kind of regression. It's simple, and simplicity means that it's generalizable. Imagine you have two tools, a very complex tool that is very, very niche and very useful for a particular use case, versus just a simple tool that works for every circumstance. Like it's a jack of all trades, master of none. A simple tool is simple and because it's generalizable. And that's why, just to emphasize to you again, why we default all our regression models to linear. So that even if you don't know what's going on in the background, you should be aware that we default to linear models so that it's simple and measures the relationship. Now, let us see what is appealing about a regression model or a linear regression model that makes it very appealing and makes it the ideal form to which we default our models. Well, for those of you who are religious, there's a concept of omnipotency, right? People talk about omnipotency of their God or their creator or a sovereign being. And for those who are not religious, that means that the power of their God ranges from minus infinity to plus infinity, right? Mathematically. Now, why is it important to you that your God possesses the property of omnipotency? Like, why is that a desirable attribute of Godship? What do you think? Why should
because with that, at any time you are safe.
Sorry, go ahead.
I said, no, with that, with omnipotency of God, it means you are safe because your God is omnipotent. It means at any situation, he can't savage you. So you feel safe with it.
Excellent. So that means that whatever the situation, right? It doesn't matter how small the situation is or how big the situation, that property of omnipotency has you covered, regardless, right? And that's why we find that property to be quite desirable. Now, of all the models we have, right, linear regression models are the ones that have that inherent property where their coefficients range from minus infinity to plus infinity. Let's look at an example. These are betas from linear regression model. Like we said, the range of the betas range from minus infinity to plus infinity, which is desirable, right? Because like the omnipotency of your creator would believe that no matter the relationship, we can be sure that it will be measured in a linear regression model, right? It doesn't matter how small the relationship is or how big it is, a linear regression model will capture that relationship. So there is nothing it cannot capture. But let's look at the outcome in a binary logistic regression, like the previous slide we talked about smoking. What are the possible range of the outcomes in that scenario? That picture, we had males and females. What are the ranges of the outcomes for that slide? We're just talking about the outcome.
0 to 1.
1 to 3.
How is it 1 to 3? We're talking about for each individual.
It's a outcome. So 0 and 1.
0 and 1. It's either you smoke or you don't smoke.
Oh no.
Yeah.
Yes, sir.
Are we all happy with that? It's that. Do you all understand why it's 0 to 1?
Yes, sir.
All right, great. Now, what are the odds? What is the range of the odds? Yes, Johnson.
0/3.
No, I'm not talking about that particular sentence context. I'm talking about in general, across the whole universe. What ranges could the odds fall in?
0 to 1.
0 to infinity.
Excellent. 0 to infinity. Because the odds you can have odds of 1 in whatever. It could go on and on and on, but the range is from 0 to infinity. So the question is, we want to convert every kind of regression so that it goes back to and behaves like a linear regression. what then do we have to do to take the odds and make it behave like a linear regression model? We don't want 0 to infinity. We want minus infinity to plus infinity to achieve that concept of omnipotency, right? What do we then have to do to make that happen?
We take the log.
Excellent.
The logarithm.
Excellent. We take the odds, the log, right? So the log of 0 is infinity, right? So, and log of infinity is infinity. So just taking the logs allow us to force the logistic regression model to behave as though it was a linear model, right? So that the omnipotency ranges from minus infinity to plus infinity. And again, why are we so interested in it having this property of minus infinity to plus infinity? Who can re-echo why? You can refer to the previous slide of you know.
So omnipotent.
Huh?
Because it could fall anywhere from lower than 0 to higher than 0.
Yeah, because we wanted to measure any possible relationships that
yes, everything is covered.
Exactly. So that is why we want. Obviously, if it's 0 to plus infinity, that doesn't help us because it means that our model cannot capture everything. Remember that the whole point of a model is to simulate reality. In reality, anything can happen, right? That is one of the things you learn in life. Anything can happen. So what's the point of a model that I cannot explain reality when reality happens? That is a very worthless model. So that is why we are interested in converting. I hate part of my voice. From 0 to infinity to minus infinity to plus infinity. And then what's the range of odds ratios?
One to infinity.
So 0 to infinity.
0 to infinity.
0 to minus infinity.
So it's 0 to infinity. So why can't we have, you cannot have minus odds ratio. So why do we need to convert the results? Remember, we fit the regression in log odds. So why do we then need to convert it back to odds ratios? It's, who knows? Why don't you just present the result as log odds?
Because we don't, you see, odds ratio is about probability. And then you cannot have a negative probability.
Okay. The answer I'm looking for is less technical. It's more along the lines of communication. Who can help us out? Why do we?
It will be more difficult to explain the outcome with log odd than using odd. It's simpler to explain with odd than using log odd.
Okay, odds ratios. We're never going back to odds. We're always going back to odds ratios now, right? So we're comparing two groups. In each group we measure the odds, right? But we said that in the case of a simple two groups, we can easily take the odds in one group, divide by the odds in the other group to get odds ratio. But when we have many variables, we obviously cannot do that. We have to account for all these variables, and so we need to fit a linear model that captures every possible relationship. Now we have log odds, but nobody in this world will understand what log odds are if we present them in the paper. So we convert log odds back to odds ratios by taking an exponent of a log odd. So again, you don't have to know all of this theory. You don't have to memorize it, but you need to understand what is happening in the background for you to appreciate what goes on in the logistic regression model. So simply put here, this is all we've explained in a mathematical form. So the outcome here, see, we're using the log odds, right? The log odds as outcome, and then the variables, the predictor variables are on the right-hand side. Again, we model and inherently result in a logistic regression model as log odds. But then we now take the exponent to give us odds ratios. Now let's move to something less technical. Let's talk about how do you interpret odds ratios. You have two options to interpret them. You can use a multiplicative scale, and here the word times must appear in your description, in your framing. So if odds ratio is less than 1, then you say x times lower odds. See, the word times is appearing, but another word for multiplication is times. So if you're using the multiplicative scale, the word times must appear in your framing. If the odds ratio is greater than 1, then you say X times higher odds. Now, if you don't want to use that scale, you can use the additive scale. And if you're using the scale, the word times must not appear in your framing. So if the odds ratio is less than 1, subtract it from 1 and then multiply the result by 100. If the odds ratio is greater than 1, subtract 1 from it and then multiply by 100. Now let's practice. But before that, let's quickly talk about how to assess for statistical significance. Here, you also have two options. You can look at the p-value if the p-value is present, or you can look at the confidence intervals if they're present. If the p-value is smaller than the threshold, so if the threshold, for example, was 0.05, if the p-value is smaller than 0.05, then you say that the result is statistically significant. Now, if the p-value is not there, but if the confidence intervals are there, you have to look for the confidence intervals to see whether they include the number 1. 1 means the null value. Like 5 over 5 equals 1. 4 over 4 equals 1. So whenever you have 1, that means that the number at the top and the number at the bottom are the same. In other words, the two are not different from each other. So that's why when you're looking at the confidence intervals, you're trying to see if it includes the number 1. If the number 1 is there, that means that the results are not statistically different from each other. All right. We'll practice some of this in the next few slides. Now, how do you report the results? What should you report when you're talking about odds ratios? We follow a guideline called STROBE. STROBE is an acronym that means strengthening the reporting of observational studies in epidemiology. STROBE has guidelines for how we should report things, including results from odds ratios and all of that. So this is the STROBE statement. So please, when you have time, download the STROBE guidelines and read through it carefully to see what needs to be there in your methodology or in your whole paperwork. So there's the introduction, there's the methodology. For methodology, you're supposed to provide number of participants, the variables that you selected, the outcomes, the exposures, the predictors, the potential confounders, and how you selected them. That's important. And then the statistical methods, you're supposed to describe all statistical methods, how missing data were addressed, and then to also provide your descriptive analysis. In the main results, you're also told to provide both unadjusted estimates and confounder adjusted estimates. We're going to see all of those things in a minute. But the point is that what I really want to emphasize is, especially for those of you who are doctoral students or master students, please, you have to adhere to this criteria to the letter, to the T, right? Provide odds ratios, both unadjusted and adjusted, right? Don't just provide the adjusted. We need to see how the various indicators confound the relationship. So please provide all of those things as specified in the STROBE guidelines. So please take your time and read the STROBE statement so that you have a clear understanding of how to report data or results from your analysis clearly. So this is an example here. So this here shows the predictors of mental use among current cigarette smokers. See, the sample size is clearly indicated here. This is the characteristics. This is the categories clearly indicated here. You can see that the reference group is clearly identified, right? Every variable has the reference group clearly identified. These are the crude results or the unadjusted results, and these are the adjusted results. See, everything is clearly defined. You have the odds ratios provided with a 95% confidence intervals. Please, you don't have to provide both the confidence intervals and the p-value. The confidence intervals are more important to us than the p-value. We don't care about the p-value. The confidence interval helps us to see the variability and how wide they are. So it provides us more information than just the p-value. So please, where you have a choice, always default to reporting the confidence intervals. And so this is how you want, this is just a summary of what that statement was saying. Provide the variables clearly, provide the levels and which are the reference groups, and please provide both the adjusted and the unadjusted results so that we can see to what extent there was confounding. All right, now practice time. Let's see how much you've been following. Let's see the case study number 1. These odds ratios were calculated for group A with group B as reference group. The outcome is self-reported current cigarette smoking. Who can interpret what these odds ratios are? Why have you guys suddenly gone very quiet?
Yeah. The group with the exposure have less 50% chance of risk of.
See, the problem is that you're using taboo words already.
The chance.
We have just said this now.
Yeah. So group A have 0.5 times likely to.
0.5 times what?
Likely 0.
No, we are not accepting that.
All right, so
Group A has.
the odds of smoking is 50% less in group A compared to group B.
Okay. What's another way of saying it?
The odds of group A is 50% lower compared to B.
Okay. So you're using the additive scale. What about the multiplicative scale?
Okay, on that one, you would see the odds of A is 50 times, is 0.50 times lower compared to B.
Okay.
No. I think it's the odds of group A is 0.5 times higher than the odds of group B who are currently smoking cigarette.
Where did you get higher from?
It's lower
This
now.
is less than 1. So
this is less than 1.
I think you have to.
There should be no higher.
less than
Just
1.
say times.
It should be less than 1. I mean, it's less than
The
1.
more higher should go out.
They are 50% less.
In addition
less.
to that, our credible interval.
Just 50% similar to group B.
Okay. So I want somebody to now, and all of you are just ignoring. You're all just pretending.
That's what I'm trying to say. That is a credible interval has 1 included, meaning it's telling you the 0.5. There's some level of uncertainty here, and that means the validity of this result is.
It's not significant. It's not statistically significant.
Yeah.
Okay. Now somebody, I need one courageous person to take all these things we've said and give him a very clean framing that takes into account the point estimate and the confidence intervals and clearly uses the right terms.
All right, I will do that again.
Go ahead,
so using the not the multiplication this thing, I will say that the odds of smoking in group B is 50 in group A is 50% less than group B, but the difference is not statistically significant.
Okay, excellent. I mean, I have a small problem with your stuff, but I'll come to that later. Okay, what of the multiplicative?
Yeah, someone should go for that. I'm not sure about that.
Okay, let me do that.
Go ahead.
Group A is 0.5 times lower odds of coming down with of cigarette smoking compared to group B, and the confidence interval shows that is not statistically significant.
Okay. So multiplicative. So you've all said it correctly, but again, let me there's some issues I had with that, so I'm going to correct that here. Individuals in group A have 0.5 times, so multiplicative is times. The word times must appear if you're going to use that scale. Individuals in group A have 0.5 times lower odds of reporting being current cigarette smokers compared to those in group B, but the results were not statistically significant. Now, the problem I had with the first person who answered was the outcome is self-reported current cigarette smoking. You have completely ignored that fact, and you are saying the odds of being smokers. Reporting being a smoker and being a smoker are two different things, at least epidemiologically, right? Because there is the issue of measurement bias and the inherent contradictions with self-reports. That part is not a trivial issue that you just toss aside. it has to be reflected in your answer. So you see, the odds of reporting being current cigarette smokers, right? That's how we could report that here. Or on the additive scale, we can say individuals in group A have 50% lower odds. See that the word times does no longer appear here, right? But the results were not statistically significant. All right. Based on that, who can give us the multiplicative interpretation with this one here?
Okay, if no one is going, I'm going to do it. So this one, it says that the odds is 0.6 times lower compared to group B, and the result is statistically significant.
Okay.
No. I think it is the group A are 0.6 times lower than group B, reporting being current smoker, but the result is not statistically significant.
That's wrong.
Statistical significant.
That is wrong.
Statistical significant.
That's wrong.
Significant.
Sorry.
One is not. It's not crossing one.
Okay. Go ahead and say it again. The same person who spoke. Can you repeat yourself again?
We're out to leave a smile on the commercial bus driver.
Okay, somebody else then.
All right, using the other scale. So
no, I want the same answer you said, but just correct yourself.
Okay, for me, I said it's not significant.
No, I want the sentence repeated.
Let me take it.
Okay. The odds of smoking in group A is 0.6 times lower compared to group B for self-reported current cigarette smoking, and the result is statistically significant.
Okay, great. I wanted to repeat because you omitted the word odds in the first time. That's why I wanted you to repeat again.
Okay. Yeah.
So what of on the additive scale? How will you interpret this?
So that would be 60% odds lower compared to group B.
That is completely false.
Sorry. 1 minus 60.
Minus 1.
Yeah, 40%. 40%.
Excellent. All right, that's
40% lower. Yes.
All right, that's correct. Now let's move on to. All right, let's go to more complicated one. Who can explain this one on a multiplicative scale?
This should be easy.
Okay.
The odds.
The odds for self-reported smoking was 2.6 times lower in group A when compared to group B, and the results were statistically significant.
That's very false.
The odds of group A.
Yes, go ahead.
Individuals in group A have have 2.6 times higher odds of reporting being current cigarette smokers compared to those in group B, but the result is significant.
Why did you use the word but? And?
Okay, no need for but, because the result already is significant.
Okay, great. What on the additive scale?
On the additive scales, we will say, well,
2.6 minus 1.
That's a trick question. I put that so
it's very tricky.
That's
You would say
1.6.
individuals in group A have 1.6
higher
odds.
The group in group A has 160%. Has 160%. Yes, has 160% increase.
Odds.
In group A compared with group B.
Okay, good.
And being a self-reported outcome, and the result is particularly significant.
Excellent.
In that the value of one is not included.
Somebody was saying 1.6. Why is it not 1.6?
because
Just for
you
the
need,
adjective.
you need to remove one, you need to subtract 1 from 2.6 and then multiply by 100.
Excellent. All right, you guys get it. So that's the whole idea there. Now let's critique some of the things that you should never do. Oh, I meant to add the names of these individuals, but I forgot. So, but anyway, let's just focus on this. Is just fair criticism. Not they did great science, but it's just like how do we improve the writing? In general, let's see. Let me just read the sentence here. Analysis by a multinomial logistic regression model with parasitic infection as outcome revealed that child residential area and mother's occupation were positively associated with intestinal parasite infection at a 5% significant level. What are the problems with that statement? First of all, the outcome was binary.
Can you repeat your question again?
All right. Did you hear my reading of the sentence, or should I read
No.
it? Okay.
Yeah, you can repeat it.
Okay. The question was, what are the things wrong with that sentence that starts from here to here? It starts from the analysis by a multinomial logistic regression model revealed that child residential area and mother's occupation were positively associated with intestinal infection. So the question is, what is wrong with that?
The first thing is that the analysis is binomial and not multinomial, because
excellent. So it's binary logistic regression. The outcome was binary.
Yeah.
So it is completely wrong. Multinomial regression is completely different. We're going to cover that in week 4. So again, that is not what was done. So wrong terminology. What else is wrong?
The outcome is not stated.
The key value is not supposed to be there.
Sorry?
The outcome is vague.
No, the p-value is fine.
And you see,
the outcome is not well stated. The outcome is not well stated.
Okay, sure, we can forgive them, but what
not
is
well stated?
What is just so let's leave aside the smaller issues. Let's focus on the big ticket items.
Okay,
what else is wrong there?
Hello.
There is no confidence interval.
There are confidence intervals there.
On the significance level.
Less than 1.
So
it should be 94.
It should have added that is self-reported outcome.
Okay.
Right, yes, and we don't know which one is greater. What odds is you didn't interpret the odds.
Okay, already. One house.
Okay. The odd was not applied.
Hello.
All right.
They use the word positively associated when the confidence was less than 1.
Excellent. When you say positively associated, what does that mean?
Increase the likelihood.
It means
increase the likelihood.
So what did they actually mean to say here?
That all these factors increase the likelihood of getting parasitic infection.
Now, instead of the word positively, what word did they actually mean to say?
Negatively.
Negatively.
Higher risk.
We don't necessarily say negatively. So what do we use?
Increase
likely.
Decreases.
Increase odds.
We say inverse.
Inversely.
So they meant to say, and this is why you should try to avoid big words, big grammar. Like just stick with small words. Like if you don't know what the meaning of it, well, just say that word was completely unnecessary there, right? But you see, by using words that you may not know their meaning, you end up running into trouble. So my point is, please avoid big words. Just stick with small words, and the point is to communicate clearly. So that's problem number 2, right? The bigger problem, which I'm surprised nobody has picked up, is what is a comparison group? Remember in our example here, we said individuals in group A compared to those in group B. You must provide a comparison group in your explanation. Otherwise, there is absolutely no context for it. Here, they just told us that people who lived in residential area and those whose mothers' occupations were civil servants Okay, but we don't have context. Compared to what? So each group must have a comparison, right? That is also very important to indicate. So those are some of the problems. Again, if the authors are here in the audience, Mr. Ezekiel, we're not trying to drag the paper in the mud, but this is just a learning opportunity for us to improve on how we conduct things. And then in general, we also report odds ratios to 2 decimal places, not 3, but that's not such a big deal here. All right. Here, let's see. What are some of the issues that we have here? The same problems. They say factors that were associated with malaria death included acidosis, the first 72 hours, and so on and so forth. But again, the same issues, right? You are providing odds ratios without providing us a reference group. That means the results are completely, we cannot contextualize it because because if you change the reference group, the result will change. So you have provided us zero context with which to interpret your results. Note also here that the confidence intervals are, for this result, range from 3 to 66.9. What does that tell you about the sample size?
Very small.
A small sample size.
Exactly. With small sample size, you're going to have very wide confidence intervals. And then here, this is a different problem altogether we want to highlight. The results underscore the importance of low preoperative packed cell volume. Let's see. So results. Let's see. Logistic regression analysis demonstrated that this remained a significant predictor of so here, essentially, the methodology is not provided in how they got the results, but there's something else I wanted to demonstrate in one of them, which was, let's see, I believe it was this. So here, they say novel predictors of short-term outcomes in the updated models included body surface area and insurance payer type. So here you have a study where you provide results, but no odds ratios or confidence intervals. So please, don't turn your paper into one where there are no measures of association provided, or ones where you provide only p-values, which is also very common. People will say the following factors were associated with cigarette smoking: age, p equals this; sex, p equals this. Like p it's completely useless saying that, because the p-value is trying to tell us whether the results are associated, but you've not provided us the results. It's like giving us a dish and a spoon without the food. It's like, what am I supposed to do with the spoon? Use it to hit your head and smack you. So you have to provide context, right? Like the p-value is completely useless without providing the context, the results for which you are providing the p-value. So please don't turn your paper into p-value paper. Provide the odds ratios and also provide the corresponding confidence intervals. Now, here's another problem from Stack Exchange. What a negative odds ratio means here. That this individual is saying, can you give me an intuition why odds ratios could be negative? What is this person completely missing? They're asking a question about odds ratios, but what are they actually looking at?
The logs of odds ratio.
They're looking at the logs.
Can odds ratio be negative?
No.
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 Unlikely.
Coefficients that can be negative.
Can log
But
odds
the logs can be negative.
And why do we want log odds to be negative? Refer to the concept of potency.
Yes, because we're using log odd because we want it to capture all form of realities.
Exactly. And why do we desire that the odds ratio not be negative?
Because of technical.
Because to ease reporting.
Exactly.
And so we need to convert the log odd, yes, to reportable content.
Okay, I believe you guys all know this stuff now, so that's great. Let's move on. So golden nuggets. These are some things you want to keep in mind. Use odds ratio when the outcome is rare. When the outcome is not rare, which is when the outcome is common, please don't use odds ratios. Use prevalence ratios. We'll talk about that in a minute. Check for the extent of missingness. Remember that when you do a regression analysis, what happens is that there's listwise deletion. That means that every single variable with it, every single observation with any missing value for all the variables, for any of the variables are deleted. So you want to make sure that you consider extent of missingness. The codes matter. If you code your variable as 0 or 1, you're going to get a completely different result than if you code it as 0 and 100, right? So you want to make sure that code it as 0 and 1. 0 is the outcome was not observed, and 1 if it was observed. And we'll show you in a second how that matters a lot. Choose the reference group wisely. The reference group could be based on what has typically been used in the literature, or the group with the largest sample size. That way you can ensure that the confidence intervals are not too wide. Now, one of the things you also see in some models is that they will say, oh, we use backward selection, we use forward selection. Who has heard of that concept, and why is it so wrong? Forward selection, backward selection, and all the other selections. Why is it so wrong, and why should you never ever do that? Has anyone ever used any of these terms? Please confess now and let us put you to public shame, and then you can explain to us why you did it and why you should not do it. Anyone has used that before? I'm sure nobody will agree now. Alrighty. Who wants to explain? Okay, you may not have done it, but who wants to explain to us what that is and why it's such a horrible idea? Yes, I'm Daniel. You are muted, by the way, if you're speaking. Okay. So, forward selection. Okay, go ahead.
Okay, so actually, I try.
I've heard of it. Thank you, Prof. I've heard of it, and what I know about it is aware of knowing whether a factor, a variable, is a predator variable, exposure variable, has a significant effect on the outcome. So you impute variables and check the outcome, whether it's also risk ratio and all that. But I really don't know why. I mean, I don't know what is wrong with it. That's the issue.
Okay, let me explain.
Okay,
Thank
so
you.
I think the thing is that it is about model building. Okay, because after a logistic regression, we want to build our model, and we want to select the predictors and then the outcome. And so method of using forward selection means we'll determine the significance level of each predictors. Then we'll now start adding them based on their level of significance. Okay? That is forward selection. Then backward selection is we'll put all the significant factors into the model, and then we'll start removing one by one. That is backward selection.
Okay, great. That captures the essence. Imagine we've been comparing our models to an apple. Imagine you hired an artist to create this model for you to simplify reality, and this guy actually blindfolds himself, and he has a whole bunch of colors, and he's just randomly selecting any color that he picks on, and he's like, oh, that's the color that will be used. Like, dude, no, that is wrong, right? Apples have you need to be intentional about how you select the colors. You can't just select any color and that's an apple. That doesn't make any sense. So we need to
yes, because yes, because I think that is right, because what is statistically significant may not be clinically significant. So in building the model, some clinical significance has to come in, okay? Even if it is not statistically significant. So using backward and forward selection is like just depending on statistical significance rather than biological significance of the predictors.
Excellent, excellent. So the point is that model building should be based on deep subject matter knowledge. Don't just rely on the computer. So in forward selection, you're saying, oh, we're just going to throw all these variables we have in our data set, and we'll just keep on seeing, oh, how are they significant, right? Backward selection is like, oh, we'll just start adding one by one and see whichever is significant, we will keep, whichever is not. It's like you have completely blindfolded yourself, and you have completely exported your thinking faculties to the computer to do your thinking for you. Like, no, please, it's a great thing that you don't know what backward selection is or what forward selection is, so that you don't do it. if you want to sit down and fit a model, you need to sit down and think through the science. And we're going to talk about that in a second. And so model building should be driven by deep subject matter knowledge, not just by whether a variable is significant or not significant. We want to achieve parsimony. Parsimony means that our model doesn't have too many variables, because we don't want a model that is overfit. Because then it doesn't really explain reality. It's not simple, and it ends up capturing a lot of noise. The goal is to include all confounders and to exclude all collinear variables. We'll talk about what that means in a second. If you're doing a lot of exploratory analysis, you should consider using 99% confidence intervals so that you're more conservative and you reduce type 1 error. And then with weighted analysis, we'll talk about weights. So I'm going to leave that for a future session about weighted analysis, because that's a lot to unpack. And please don't report log odds in your results. Report odds ratios so that people can understand and follow accordingly. So this is to explain to you why you are encouraged not to use odds ratios when the outcome is common. So remember that the formula for odds, we talk about the formula that connects odds and prevalence. Odds equals to prevalence all over 1 minus prevalence. Now, when the outcome is very rare, the odds and the prevalence are almost the same. So with the prevalence of 1, the odds is 1%. The prevalence of 10%, the odds is 11%. With the prevalence of 50%, the odds is 100, right? So you see that when the outcome is common, the odds ratio is always exaggerated, and that is not a good thing. And that's why we say that when the outcome is common, please use prevalence ratios and not odds ratios. So here are some basic do's and don'ts. Do's: use 1, 2, 3 rule for decimal places. So generally, we frame percentages to 1 decimal place, odds ratios to 2 decimal places, and p-values to 3 decimal places. Always include the comparator. Don't write as though there was no context. Like, don't just say the odds were higher among, this group and that group without giving the reference group for each comparison. Display the confidence intervals, please. Again, that is more informative to us than just the p-value. And according to STROBE, try to show both the crude and adjusted odds ratios in the tables. Now, some don'ts. Don't use odds ratios for common outcomes, please. Again, odds ratios tend to exaggerate the outcomes relative to the risk ratio. So use prevalence ratios, which are more conservative. And please don't say almost significant. Significance is like pregnancy. You're either pregnant or you're not. There's no middle ground. So once you've defined your threshold for statistical significance, you should stick to it. Don't suggest causality with the way you frame your results. Don't say odds increased with increasing age. That almost suggests as if you followed people over time and you could see the odds increasing over time. Instead, you should say odds were higher. And don't show only p-values in the paper, please. You should report the percentage of the odds ratios that generated the p-values. So these are just some basic do's and don'ts when reporting odds ratios. Now, for those of you doing meta-analysis that you might get results from different studies, I want to pull them together. You should strive to convert odds ratios from previous papers to relative risks so that you can make the results comparable. Remember that odds ratios tend to exaggerate things. So comparing odds ratios with risk ratios is like comparing apples to oranges, right? We talked about prevalence ratios. If you want to calculate prevalence ratios, you can use the Poisson model, and that actually calculates prevalence ratios or the incidence rate ratios, which are analogous to relative risks. So for those of you who might be doing a meta-analysis, I wrote a small program for you. Let me show you how that works, that you can use for your work. So it's a small Excel program that allows you to make direct comparisons between the odds ratios. I've provided instructions for you here. So essentially, you take the odds ratios. So an odds ratio of 1.07 corresponds to a risk ratio of 1.03. So you can see that when the odds ratio is small, or when the prevalence is small, you see there's a very close link between the odds ratio and the risk ratio. So an odds ratio of 1.01, you have a risk ratio of 1.004, quite close. But as you can see, when as the odds ratio starts getting bigger, an odds ratio of 15.04 corresponds to a risk ratio of 3.8. Can you imagine that? And then As you get higher, an odds ratio of 915 corresponds to a prevalence ratio of 30.2. So you see that there are huge differences. So I'm going to share this. It's a small calculator you can use. So you just look for the odds ratio you are looking for, and you just grab the corresponding prevalence ratio. If the odds ratio is less than 1, you can simply take the inverse, and that gives you the corresponding value you're looking for. So you can play with this when you get it, but that will be disseminated to you after the class as well. All right, so that's the major analytic consideration. Now let's look at our case study for our study. So here we're looking at the association between smoking cessation and weight loss. I have already provided the context for the study, but essentially what happened was, this is the NHANES. This is a national survey in the US. NHANES stands for National Health and Nutrition Examination Survey. It was a follow-up survey of individuals aged 25 years or older. The baseline survey was in 1971 to 1975, and the follow-up was in 1982, about 10 years later. They collected self-reported data on smoking, and as well as the way the individuals to get their weights, both at baseline and at follow-up. The data set I shared with you on our LinkedIn page has records for 1,556 cigarette smokers who completed both baseline and first follow-up survey. So the question we're trying to explore is really, what is the association between quitting smoking and weight gain or weight loss, depending on how you want to look at it. Now, remember we said earlier that when you're collecting data or when you're analyzing data, you don't just want to do backward selection, forward selection. No. We don't want to see that. Model building should be based on a thorough understanding of a subject matter. So you need to first of all sit down and create what we call a DAG, a directed acyclic graph. Sounds fancy, but it's not complicated. So what kind of variables should be in your model? You want to include these variables, the exposure, obviously. You want to include the outcome. You want to include confounders. Include all confounders if possible. You want to exclude collinear variables. So let's explain what these things are. So you have the exposure and the outcome. The relationship we really want to measure is this arrow from here to here, right? This is what we call the causal pathway. How does exposure lead to the outcome? Now, that is what we want to measure, but we have to worry about other things. A confounder is a variable that is associated with the exposure independently and is associated with the outcome independently and does not lie on the causal pathway, right? Take, for example, a variable like physical activity. Physical activity is associated with exposure. Remember, our exposure here is quitting smoking. Our outcome is weight gain. And the first confounder we're looking at is whether you are obese or not, or physical activity. So physical activity, let's stick with that. So somebody who's physically active is health conscious, right? And they may be more likely to quit smoking. Somebody who's physically active is also more likely to maybe lose weight. So there's definitely an association between physical activity and the outcome, which is changing weight, as well as with the outcome, which is quitting smoking. And this physical activity does not lie on the causal pathway. So it's not, in other words, we're saying that it's not as though you quit smoking and then your physical activity changes and then that leads to the outcome. It does not lie on the causal pathway. So this is a confounder, a variable that is independently associated with the exposure and with the outcome and does not lie on the causal pathway, right? A collinear variable is associated with the exposure, but not with the outcome. You see that? The covariate is associated with the outcome, but not with the exposure. So what we're saying is that when you're fitting your regression models, you want to sit down and critically look at what variables are the exposure group, what is the exposure variable, what is the outcome variable, and what are the confounders. So you have to list all the confounders, right? This is what we mean by saying that you should have a solid understanding of the relationship and solid understanding of the subject matter. This is more important than any forward selection, backward selection, or any flips you are doing, right? With just statistical, you need to understand data. And so at the very least, this is what we expect you to do. You understand why you selected certain variables and how they relate. Now, what is the difference between confounding and effect modification? That's something people get confused all the time. With confounding, we're comparing the crude results versus the age versus the adjusted result. So let's say we say that age is a confounder of the relationship between quitting smoking and weight loss or change in weight. So in other words, your age, if you are older, for example, you might be more interested in quitting because you feel like, wow, I'm staring at my mortality in the face. And if you're older, you're also more likely to gain weight through whatever biologic mechanisms. And of course, age is not on the causal pathway. It's not as if you quit smoking and then you grow older and then you gain weight. That does not make any sense. So in that case, we can say that age is a confounder of a relationship between quitting smoking and changing weight. So when we talk about confounding, we're saying we're going to compare the crude results versus the age-adjusted results. So in the crude results, we're just looking at, in our regression, looking at the relationship between quitting smoking and changing weight only, no other variable included. And then we then add age to our regression model to adjust for age. And then we now compare what is the coefficient when we did not include age and what is the coefficient when we included age. If there's at least a 10% difference, we then say, oh, age is a confounder because when we added age, the results changed, right? So that's just a quick rule of thumb for you to know that, you know, the variable is a confounder. So we also call confounders on, you know, nuisance variables because they distort the relationship between the exposure and the outcome. So for confounding, we're comparing crude versus adjusted. For effect modification, we're comparing the results in different strata. So let's say that we're saying that the relationship between quitting smoking and weight change varies based on your race, ethnicity. And we have a biological explanation for that. We say that maybe Blacks have a higher bone density, or maybe there's some biological explanation. And so we expect that that relationship will be different, maybe between males and females, or between, you know, different races. So we look at the relationship between smoking and quitting smoking and weight change in each of those strata, right? That is what we call effect modification. So bear in mind that both confounding and effect modification involves comparing two things, but what we're comparing is very different. For confounding, we're comparing crude versus adjusted. For effect modification, we're comparing the results within different strata. All right, so in our regression model, you already have the data. We're going to share the code with you for both theta and R. Actually, I have the code here, so let's see. So you're going to get access to this to see how. So just simply copy let me dump the code here. It's a Google Doc. So provide the code. This is the logistic regression. This is the data here. You can access the data. This is the code in theta here. And this is the code in R, right? So simply follow through, depending on whether you use whichever language you're familiar with, doesn't matter, and see how the result changes. But overall, the point is that let's look at the quick let's look at the data in theta here quickly to see what we did here. Let's look at the final model and make sure that we can understand it clearly. So here, we're looking at the relationship between quitting smoking. So if you're using theta, this is how the command works. Let's just focus on the command and how the syntax is so that when you're doing later, you understand what we mean. Logit is a command in theta to fit logistic regression. If you're using, there are two commands in theta, logit and logistic. If you're going to use logit, make sure you put OR at the end. OR stands for odds ratios. So logit must go with OR. If you don't want to use logit, you can then use logistic, in which case you don't have to put OR at the end. The outcome is the first variable that has to be there. So here we're looking at weight loss of 5% of more of the baseline body weight. So it's a binary variable. At follow-up, did you lose 5% or higher of your baseline body weight? Yes or no? That's the outcome. The outcome variable must come first, right? And this is why we call it the left-hand side variable, because it's on the left-hand side. All the other variables then come next, right? So these are the other variables. this is an example of a multivariable analysis or an adjusted analysis, because remember, the relationship we're interested in is between this variable and this variable, right? So if we just had a regression analysis of these two variables, let me put it here. If we just had the regression analysis of these two variables here, this is what we call a crude analysis, right? Because this regression analysis includes only the outcome and the predictor of interest. It does not account for any other variable. So you can see the odds ratio is 0.75, right? So that means that those who quit smoking were 0.7 times, had 0.7 times lower odds of losing 5% or more of their baseline body weight compared to those who, who did not quit, right? So, or however you framed it. But the point here is, the point I'm trying to make is that here, this is crude, and the previous model is adjusted, because here you can see all these other variables that we've included in our model. We've adjusted for your sex, your race, your age, your education level, the smoke intensity, the number of years you've been smoking, your exercise levels, and your level of activity. How did we select those variables? Again, we based it on our understanding of a relationship between smoking or quitting smoking and weight change, right? We looked at confounders of that relationship. So first things first, we need to understand that when we say that your regression analysis should include crude and adjusted, this is what we mean. So in this case, this model accounts for all of those things. So in this other one here, we're just looking at gain, weight gain, as opposed to weight loss. So you need to frame things in a way that is easy for you to understand. Should I frame that as gain in weight or loss in weight? That's a decision you have to make. But in general, people understand bigger odds ratios better. So an odds ratio of 2.22 is easier to wrap your brain around. So it's easier for me to say that people who quit smoking had 2.22 times higher odds of gaining weight compared to those who did not quit, right? As opposed to saying they had lower odds. For some reason, our minds find it very hard to wrap around the concept of inverse relationships. So I would generally advise that try to frame your results, again, from a communication perspective, in a way that reflects higher odds, because it's just easier to communicate it that way. So that is one thing you have to note here, that just communication-wise, higher odds ratios bigger than 1 are easier to explain. Now, in the code here, take note that the reference group in Stata, I dot means that use the smallest one as a reference group. So I dot means use the baseline. So if the groups are 0 and 1, the smaller one, which is 0 group, will be used as baseline. But I can also say IB last. IB last means use the last one as a reference group. So if the groups are 0 and 1, the last is 1. So 1 will be used as a reference group. But I can also specify the exact group I want. So here I say IB2.exercise, saying use the second one as a reference group. So that, of course, if the groups were male, female, and other, the second group is female, and so it will be used as a reference group. How do you choose your reference group? Well, see what other people have used in the past, so it's easy for you to compare your results. Or you can use the group with the largest sample size as the reference group. When we don't put any I dots in front, that means that we are either assuming that that variable is a binary variable, in which case the lowest is being used as a reference group, or that is continuous. So the interpretation is per unit increase. So that's how you interpret it. So now, if you just want to format this and put that in your paper, you can then simply copy this. So again, when you look at the code, you will have the codes for Stata and the codes for R. So just, you should try and make sure that you practice. Again, practice makes good. So in that case, you just paste the result there in Excel, and then you can format them accordingly. So here, I will then say, this is fixed. I want to fix this to 2 decimal places. I want to fix the lower confidence interval. So remember, we care more about the confidence intervals than the p-value. Fixed. again to 2 decimal places. And lastly, let's fix this to 2 decimal places. We can then apply that change to all of them. And then we can then format them properly. And we take the first one, the confidence interval, and then the other one. And so we format them as the odds with the confidence intervals. And now we can now just, remove the missing values. But essentially now we have the odds and the confidence intervals together. So now you don't need the p-value because, again, like we said, the confidence intervals tell you everything you need. But this is again just how you could format it in Excel and then copy it into your Word document. All right, I've spoken enough. Any questions? So next week we'll focus a bit more about issues of. Next week we'll go back to the DAGs, but we'll place a lot more importance on how do we consider these things when we're collecting the data, right? Because this becomes even more important than you don't want to have a situation of medicine after death. So how does this come into play when we now want to design our study? Like, how should we consider DAGs when we're collecting data? We'll focus a lot of attention on that next week. All right, any questions?
Well, sir.
Yes.
Prof, thank you so much for everything. You've actually done a great job. You've imparted a lot, but I have a lot of questions. But I would love to go over the recording again. By next week, I'll be able to ask my questions, sir.
All right, sounds good.
Yeah.
And if a lot of people have questions, we can, again, repeat some of the, you can drop your questions and we can try and address them in the next session. So, because, this is a lot to cover, obviously. I've tried to provide just the high level things that you need to know. But even at that high level, you might still have questions. So we can definitely cover them, we only have one.
A quick one there.
Yeah, go ahead, please. Yes.
The confounder, does that act like a moderator variable?
The moderator variable is no, this is the moderator up here, the mediator.
Okay. That's fine.
Sorry, can I say something?
So I have a
Sorry.
question, sir.
Sorry, can I say something?
Go ahead, Lingley, please.
Yeah, so because I see some people are leaving, can you please complete the survey, the evaluation survey before you leave? I've just posted it and I will post it again. Here it is. For certificates, please do not, again, I repeat, do not provide your email addresses here. I am posting a survey for that purpose. I will need you to please click on this link that I've just shared now, and then you will add your name and email address. There is a space provided for that. If you share your email address here, I will not consider it for certificates. Thank you.
Thank you. Can I speak? I've been raising my hand.
Please go ahead.
Can I talk?
Yes.
Okay.
I actually have no question because I'm lost. Okay. I have been lost from the beginning. This is because you started the presentation with questions and people, were giving answers, meaning that they have prior knowledge about what you are taking us. Now, do you have a class for novice like me? Not a beginner in this case now, novice, because anything outside frequency distribution and tables, then it becomes, it becomes like mumbling. I don't know how to explain it, but
I understand you.
I need a starter class for regression analysis. So is there any webinar for that?
Okay, so what we'll do is that we'll have after this episode. So first of all, I encourage you to just hang in there, but we're going to have another series for complete newbies. So that will be taken things from like as simplifying them to the extent possible. So we'll have that and we'll advertise it as soon as we prepare it. So you can definitely join that. But I'll still encourage you to join this one to the end too.
Oh, okay.
Yes, sir.
Thank you.
Sir, I have a question, sir. Sir, I'm raising my hand. I have a question, sir.
Yeah, you all have.
Thank you. Thank you so much for the. But I really learned a lot. So I've been doing an analysis, and I encountered three challenges, which I would like your clarification, sir. One is that in one of the analysis, my odds ratio was 0, and I found it difficult to interpret. In another one, the odds ratio was, I wasn't clear because the odds ratio was like 750 in the comparison, like between the reference group and that is between A and B, one was 750 times higher. So I was wondering if that one was how to even interpret it or whether to just drop it. Then the third one I would like your clarification is that what I'm analyzing, the person used yes, no, I don't know. So I want to ask that using 1 for yes, 0 for no, and 0.5 for I don't know, is that a good way to code, sir? Thank you.
Okay, last question first. No, that's not a good way to code. If it's a binary logistic regression, you have to decide what to do with the don't know. You can set them to missing, or if that is something that is meaningful. Don't know, depending on the context, can have meaning. If it's like smoking, do you smoke? And the person says don't know, that is not very meaningful. But if it's a question like, do you think COVID-19 vaccine causes heart attack? And the person says, don't know. Now that don't know at this point is meaningful because it's like, yes, no, don't know. So it depends on the context in which don't know may be meaningful. So in that case, you obviously want to preserve the don't know because that has valid interpretable context. In which case you're not looking at a binary logistic regression anymore, but you're looking at another type of regression like a multinomial regression. So
yes, multinomial. No, multinomial.
So don't code it that way. The second issue is that if your outcome was binary and you're getting odds ratios that big, either means that your outcome is very common, in which case you should not have been using a binary logistic regression. So in general...
No, so I was using multinomial, sir.
Okay, multinomial. Well, that means that your sample was very small.
Oh, my sample size, the sample was like 383, sir.
Well, that could be small in some context, right? So you have to determine what's the sample size you need for. If you have a regression model that is packed full of variables, remember that we want our model to attain parsimony, which means that we don't want to have too many variables in the model, right? There has to be a careful selection of variables. So 300 may seem like a big number to you, but it may not be big in the context of the research you're doing or relative to the number of variables that are in there. You might have an overfit model where there are just too many variables and just too much noise in the model. So you have to go back to these basics and say, what variables do I need? And what is the sample size that I actually need to explore those relationships? So, and then definitely, if that is a problem still, then you might want to look at another kind of model. You might want to, for example, dichotomize the variables and use a prevalence ratio instead, which tends to be more conservative and hence more interpretable as opposed to an odds ratios. Because remember that even the multinomial regression is still odds ratios. We call it a multinomial logistic regression. It's still a logistic regression. And so it still suffers from all the issues with a binary logistic regression, namely that the odds ratios tend to exaggerate things. I hope that is clear.
Yeah.
Yes, sir. So the last one was, can we have odds ratio of 0 and what would it imply?
Mathematically, yes, but practically, no, it's not. Almost impossible because it could be 0.00 something. But it means then that the relationship is extremely small. So maybe it's 0 because it's from rounded to 0. So theoretically, of course, we can have 0, but practically, no.
Yeah.
Okay.
Hello.
Thanks, sir.
Yes.
Hello, sir.
Yes, go ahead.
So just like one of us has stated, I'm practically not a newbie, completely newbie, but I've been using SPSS and R Studio, but I tried to get Stata and I found out that I couldn't. I don't know if there's a way that we can get a help around it, or do we have to really pay does it have to be with a license or something like that?
So
Because we need to, yes.
So let me understand this. You're asking me whether we should provide you with data licenses?
I was just asking,
understand the question.
Is there a way we can get a free version of it for some time for practice, even though we can't get the license, you know, like maybe things like Atlas and stuff like that. I got license for it, which I used for, I got free license for it, which I used for practice, and then it expired. So whenever I'm able to get the license, I can now, just for practice, I'm just saying.
I understand you, but just to be clear, we don't work with Stata. We don't. The fact that we're using Stata we have no relationship with Stata Corporation. So that's the question that will be best directed to Stata Corporation. That can they provide you with licenses? We are just doing a public service by providing education, but there's issues of software. We can provide you with access to the chi-squares platform because that is within our control. But we can't, as you can understand, we can't provide you access to third-party software that are not within our control. So you might want to send an email to Kais to Stata and ask them whether they can provide you with an educational license. And Lungile, please, you can share link to the chi-squares platform to folks who want to.
Okay, so does that mean we can run all this analysis using chi-square platform?
No. Not for now, but I'm saying that it's not our job to provide you with licenses. You have to go and figure that part out yourself.
I understand. Okay. Thank you.
Right. You're welcome.
My hand is up.
Go ahead.
Prof, sorry, you said something about the not really getting our in regression analysis to machine using the backward and forward issue. So there's a problem I have. Like I'm doing a study where I'm trying to predict the outcome, develop a model for predicting a particular condition, a disease condition. And we're thinking of using machine learning to develop a model. I don't know whether what you said could be, could be applicable to it. As leaving machine to do our thinking and adding and subtracting. I don't know.
Why are you using machine learning as opposed to using just a general regression? Like if I'm because that issues, right? So in general, right? The rule is do not use an ask. What do you call it? To do what a simple broomstick can do, right?
Okay.
Use the simplest method possible. So, and that's a question I get all the time, right? People are like, oh, I want to run these advanced models. I want to do this, deep learning. I'm like, and why are you trying to do that? First of all, do you understand how a simple regression works? And if no, if you don't, if you can't understand the simple one, why are you trying to achieve it? So my point is, yes, you can just go ahead with the simple regression because knowledge of fitting regression models must start with this. So what you need to do is get a piece of paper and draw a diagram. That's where you should start, right? You start with a piece of paper or your tablet and say, okay, what is the exposure? What's the outcome? What are the confounders? If you've not started like this, then you've gotten it wrong. You don't relegate the work you are supposed to do to the machine because you are the one who is the researcher, right? Don't just throw it to the machine to figure out things. So again, grab a piece of paper and try and depict the relationships on the DAG, and that's where you want to start from.
Prof, I have a question, please.
Let's go ahead.
So thank you very much for this for the lecture. You talked about we trying to use our knowledge, the knowledge of maybe domain knowledge or our expertise to understand what confounding variables are. Sometimes it might be difficult. Is it something that literature review would be able to provide us answers to? And if that is the case, what if there are where our expertise in that field did not suffice or literature review was not enough? How can we, maybe in a novel niche or a subdomain of knowledge where it's still being explored, where literature review might not be sufficient. How do we go about that? Thank you.
So again, start with a piece of paper. Again, that's my default answer. Start with a piece of paper. If you don't have any knowledge in the domain, you either should not be researching it or you should get a collaborator. One of those two things have to happen, right? So get a collaborator who is an expert in that area. And that's the whole point of collaboration, and sit down together and brainstorm. That intellectual part of study design has to be there. Study design is an inherently intellectual process. And when we say intellectual process, that is the intellectual process we're talking about, where you sit down and say, all right, this study, what do we think? What is the hypothesis, right? But the norm in studies nowadays is that studies are done with completely zero intellectual input, right? And it's like, oh, like as a journal editor, you see this all the time. Like, wait, so what's the thinking? What's the hypothesis? Like, how did you select confounders, right? So my answer will always boil back to this: get a piece of paper and sit down and say, what is the exposure? What is the outcome? What are the confounders? The relationship now, this is where literature review comes in. Is this variable truly confounding the exposure, right? What does the literature say? Is this, apart from looking at the data, right? What does the literature say about the relationship? What have other studies used in the past as potential confounders? Now, note that because a variable was a confounder in somebody else's study, doesn't mean that it's a confounder in your study, in your data set, right? That is why, of course, there's a role for literature review, but you have to think of your own special circumstances. No two studies are the same. So there's no reason why two sets of confounders should be just exported from somebody else's study to your own study. You got to know what you're studying first. And that's why you must start with a blank sheet of paper, sit down and try to provide that intellectual input, which is the first part of doing any study. And if you don't know the domain expertise, then go and get somebody who is an expert and say, hey, I want to do research in the area of, whatever, tobacco use, and I don't know anything about tobacco use. Can we collaborate? And then you have that intellectual input provided for you. All right, any other questions?
Good evening, sir.
Yes.
Okay, so please, mine is because I'm new to all this. Mine is where and where should we apply this regression? Is this for only CRT models, cohorts, survey, or like I want to get where do we this thing apply it like in which this thing type of studies do we apply it?
All right, thanks. We covered that in the first session. We said any study, right? We are looking at, there are three explanatory factors that explain anything in the world: truth, chance, or bias. That's what we covered in the first session. Truth, chance, or anything you see in this world can be explained by just one of those three things, right? It's either the truth, or it's chance, or it's bias. Research seeks to find the truth. But for us to find the truth, we have to separate the truth from chance and from bias. That's where regression comes in. So it doesn't matter the study. It's a cross-sectional study, you can use it. It's a cohort study, you can use it. So any study type where you have, you're trying to measure the relationship between an exposure and an outcome, you actually want to find the truth, which is this causal pathway. But you realize that, there are other alternative explanations. So whenever you're in a situation where you are saying, does eating meat cause colon cancer? And then you're like, but what could be other alternative explanations? Once you can think of any alternative explanation than that relationship, then that is what we call a confounder. Confounder simply means alternative explanations for what we're seeing, right? So you have to control for all of those things to keep them quiet so that we can truly measure the relationship between the exposure and the outcome. So in a nutshell, yes, you can use it for any kind of study that involves measuring the relationship between exposure and with the outcome. In other words, analytic epidemiology.
Hey, thank you so much, Dr. Gafu. I have a question. I have two questions. Thank you so much for these sessions. Are really high yielding. The first question is, when do we say that the outcome is common? It's about the use of odds ratios and prevalence ratios. Is it like an intellectual scientific perception before conducting the study, or you first compute the prevalence and then you determine whether it's common or not to use odds or prevalence ratios for the association? And then the second question is, what's the difference between ordinal logistic regression and multinomial logistic regression? Is it are they the same, or one is under the other, or they are completely different? Thank you so much again.
Welcome. Yeah. So here, see the outcome here is, so in general, the cutoff is 10%. We generally use 10%. If an outcome is 10% or higher, it's common, right? And so the result will be the result will be in general more exaggerated with an odds ratio. So let's see, for example, here, let's refit this model with an odds ratio, and then let's calculate it with a prevalence ratio, and let's see the difference. So here, this is the result with an odds ratio. Then let's change it to let's change the prevalence ratios. So here, again, this is, can you guys see my screen?
Clearly. I can see it very well.
This is the result with odds ratios, right?
Yes.
Same variables, same outcome, same predictors, odds ratios. In the second model, we've used Poisson models. A Poisson model with the binary outcome is the same thing as a prevalence ratio, right? And we've calculated the incidence rate ratios, which approximate to prevalence ratios or incidence risk or relative risk. So the first thing you notice that the odds ratio here, you see that people who smoked had 2.19 or 2.2 times higher odds of gaining weight compared to those who did not quit, after adjusting for all these other variables. So that's what we're saying. The way you interpret this variable is to say that individuals who quit, which is value of 1, had 2.20 times higher odds of gaining weight compared to those who did not quit, after adjusting for sex, race, age, education, smoking intensity, smoking duration, exercise, activity, and their baseline weight. So that's the actual correct way of saying it. You have to say all of what we just said, that individuals who quit smoking at 2.20 times higher odds of gaining weight compared to those who did not smoke, who did not quit, after holding sex and all these other variables constant, and the result was statistically significant with a 95% confidence intervals of 1.71 to 2.82. That is how you're going to say it. So we are, by including all these variables, we are saying, let's keep all of them quiet. Let's completely eliminate their influence from our interpretation, so that we cannot say that, oh, the result was influenced by sex or by age. No, because we have held all of those variables constant. So we have muted them from the analysis. So this is the adjusted result after holding all those variables constant. But that is not what I was trying to point to. Now, what I was trying to point to is, look at this result here. This is the odds ratio. Now look at the corresponding prevalence ratio. Do you see the difference? Here, you have 1.4 times, the prevalence, prevalence ratio is 1.5 times higher among those who quit compared to those who did not quit, right? You can see that this is a bigger number than this number. So again, whenever the prevalence is more than, so you see, this is when we tabulate the outcome is reported by 44.89% of the population. So this is the common outcome. This is not rare at all. So in this kind of cases, you want to use prevalence ratios because prevalence ratios are more conservative than the corresponding odds ratios. I hope that is clear.
Yeah, that's clear.
All right, great. Next question.
May I ask a question, please?
Then the difference
Please
between
go ahead.
binomial,
The lady.
multinomial, and ordinal distribution.
Yes, the lady, go ahead, please.
Okay, thank you. So when you mentioned that when the prevalence is high, we used a prevalence ratio rather than odds ratio, there is an exact number, like can we say if it's more than 10%, for example, or 20%, or it's
10%.
a gray area?
You
10%,
know,
okay.
the rule of thumb is that there's no rule of thumb, but in general, we use 10% as a cutoff for an outcome being rare or not. So if it's more than 10%, you are more conservative to use, like I showed you in that Excel spreadsheet, right?
Yes.
For every corresponding value of the odds ratio, the prevalence ratio is almost going to be smaller, right? Now, if you just want to exaggerate your results, sure, you can go ahead and use odds ratios even when the outcome is common. But for every value of an odds ratio, you're going to have a corresponding more conservative value for the prevalence ratio. And this is especially when the outcome is as the more common it is, the larger the difference. So with an odds ratio of 25.99, the corresponding prevalence ratio is 5.09. So for the first person who asked a question that, oh, they got a prevalence ratio of 700 and something, see, your prevalence ratio, your odds ratio was 717, but the corresponding prevalence ratio would have been 26.7.
Yes.
All right, next question.
Thank you.
Welcome. Yes, please go ahead.
So, am I right now? Am I
The first
right to say that
go ahead, the person speaking.
what you said with regards to the backward selection and the stepwise selection, am I right to say that doesn't let you get when it comes to
Can you type your question? We can't hear you at all. It's really scrambled. Okay, next question.
I want to ask a question. My question is the variables you copied to Excel when you were doing the calculation is quite time consuming, especially when you are putting it, bringing the confidence interval. I want to see the way you did it again. It was very fast, and then today, in fact, you are on fire. You are very fast for us today. So.
Oh, really? I thought I was being very slow. Okay. We'll give you this Excel spreadsheet so you can see the formulas are there. You can see the formula in here. Just click here and look at the top. You are going to see the formula. So we're going to share the spreadsheet with you today.
Okay.
So you can just click on it and you can see the formula. So you can just follow it in your work.
Yes. Sir. So another question of mine is that, if, for instance, very good. If you take something like sex alone and run it against the dependent variable by bringing the I dot to the sex, what type of analysis are you doing when you pick it one after the other? I think this one you run it only once after you have keying the I dot attached to all the independent variables. But when you pick it one, like sex, I dot against the dependent variable, what type of analysis is that, sir?
That's bivariate analysis. Bi meaning two variables, the outcome and one predictor. That's bivariate.
Oh, okay.
Or you can call it crude logistic regression analysis. Crude means that they're just two variables in the regression. I hope that makes sense.
Yes, please.
All right, great. Okay, I believe we've answered all questions. Or is there another question remaining?
Hello.
So
like
we're going to have a simple for those of you who cannot follow, or those who don't want to write code. Sorry, hold on a minute, please. Okay. Yes, sorry, go ahead, please.
Hello.
Yes, go ahead.
Okay, thank you so much for this session. They are really very useful and important. One comment is, of course, along the way, I think today you are quite very fast, and I know that many colleagues kept on jumping in to explain. And there was a lot of confusion, and somewhere like would get lost. What I would probably request is maybe people can be raising their hands, and like one person can speak, and all of us can assimilate and understand what they're speaking, and be able to juggle and understand, because this is quite very very useful. And then the question part, initially when I followed, I think there's one study which you presented and we observed that they just mentioned the odds ratio for the outcome and in one group, and there was no comparison. And I just asked that maybe if that was like a cross-sectional study where like there was no control group, but then later I think in some of your responses you've mentioned that regression can be used in any sorts of study, but we need to have one population where the outcome has the group. So I think probably that was already answered. Thank you.
Yeah, so yeah, that's a good point to raise. We'll improve in the process. But let me explain what I meant by the comparison group. So the comparison in this context is not saying we're talking about an analytical study where we're having an exposure on a control group. It's saying that for each line of this regression, there's a comparison group. The comparison group is the one that is missing. For example, education has groups 1, 2, 3, 4, 5. 5 is missing. That means 5 is the reference group, right? Active has 0, 1, and 2. 2 is missing, so that means 2 is the reference group, right? So what here we're saying, this line of regression, the way we're going to interpret it is saying people who quit had 2.20 times higher odds of gaining weight than those who did not quit. Here we're saying males, I don't even know what the reference group is, but let's say males had 0.91 times lower odds of gaining weight than females. Here we are talking about comparing blacks to whites. Blacks had 0.95 times lower odds of gaining weight compared to non-blacks, and so on and so forth. Here we're saying group 1 of education, whatever that group is, had 1.29 times higher odds of gaining weight compared to group 5. For this is group 2 compared to group 5. This is group 3 compared to group 5. If you don't see the comparison, then we're lost. Like, what are you comparing to? That doesn't make any sense. So within each of these variables, you must provide a comparison group when you interpret your results. I hope that is clear.
Yeah, very clear. Thank you. I believe also for everyone else.
All right, great. All right, any other questions?
There's a question, I'm not sure if you've asked. When we consider Poisson logistic regression analysis and odds ratio?
Sorry, is there a question there?
Yes, when do we consider Poisson logistic regression analysis and odds ratio?
We said that when the outcome is common, you should use a prevalence ratio. When the outcome is not common, the odds ratios and the prevalence ratio will give about the same thing. So,
yes, Prof.
Yes, go ahead.
Yes, looking at p-value and confidence interval, I'm looking at 6, and if I'm to go by p-value, I would say not significant. However, if I'm to go by the confidence interval, I would say significant. Isn't there? I don't know. Very to understand it a bit.
No, both are not. How did you conclude that the confidence interval is significant?
Because you said when it is 1, then it is not significant. But this is 1 point something. So I don't know. Is it
Interval was it lower? Let me interrupt you there, right there. Was the confidence interval ranges from where to where?
It ranges from 0.7 to 1.17.
Okay, does that include 1?
Okay, maybe I wasn't anticipating that. If it's 1 inclusive, then I get it. Thank you.
So since it includes, so does it include 1, first of all?
Yes, it does.
So we said if it includes 1, what's the conclusion?
Not significant.
Okay. Do we draw the same result from the p-value?
Yes.
Okay. So do you understand now?
Very well.
Okay, great.
So much.
All right. Any other questions?
Prof, are we going to do hands-on experience? Are we going to do hands-on
No, we are beyond the time, so we'll move that to next week.
So, yeah, hi, Prof. I just wanted to ask, like, seek your opinion on the whole kind of logic behind, let's say, stepwise, backward and all that forward and, regression stuff. So, before even going in for epi, I do see people doing that. And to be honest, I did not see anything wrong with that initially, right? But, coming up with what you said, I perfectly agree with you, but I just want to know your opinion on, do we literally have to discard them at some point? Because I feel like it's domain specific. In the epidemiologic field, we are super concerned about, variable relationship, especially when we are looking forward for causal inferences and all of those. So you could see that kind of very in-depth logical considerations within the epidemiological field. But then here are colleagues that are, especially in the natural sciences, biology, even in the social sciences, I saw them doing that a lot, like the backward, forward, stepwise, and all of that, wherein their goal is not even to explore anything causal. Sometimes they just want to explore and understand the, variable relationships. It could be a bit complicated. Couple of critics could be there from an epidemiological standpoint. But then, is it still useful in some contexts? And which of those contexts do you feel we can still hold on to them, not to 100% discard them, even for other domains beyond epidemiology?
That's a good question. So, but before I answer that, I'll ask you, right? Do you think truth is relative or absolute?
Yeah, I feel like truth is just absolute, in my opinion.
Okay. So science is all about, or research is all about measuring the truth, right? Between an experience and an outcome. So if that is the case, then the process of measuring it should be free of noise and just free of, there has to be, again, it goes back to my original point that there has to be some intellectual input in the research process where you sit down with just yourself and a blank sheet of paper and you say, this research question I want to explore, it doesn't matter whether it's social sciences because there's huge overlap between fields, right? We might have different terminologies, but what we are trying to achieve is the same, namely to capture the truth. So even if I'm looking at the relationship between, let's say, social sciences, I'm looking at how does, how I can't even think of anything that relates to social sciences, right? But the relationships are still there. Yes, I would still say, sit down with a piece of paper and explore. What are the, and even if it's exploratory, right? You should still say, what is the, what are the factors that are associated with this outcome? That step of sitting down and providing your input intellectually is very critical. Because at the end of the day, the issue is with forward selection is just saying that I'm going to sit down, there's a forward selection. I'm going to start with one variable, and then I'm going to add another variable, and I'll see if it's significant. If it's not, I'm going to throw it away. Then I'm going to add another variable, and I'll keep adding until I have a whole bunch of variables. That's a problem because you have some negative confounding, right? Where sometimes a variable is only a confounder in the presence of another variable. But by removing it off like that, you have failed to capture that relationship, right? And this process is just going on with and then some significance could be due to multiplicity. There's so many multiple comparisons going on here that you have so much noise injected into the process just because you are looking so hard. I tried the first variable, I tried 99 variables, and I'm still trying, right? Variables attain significance just because I was looking so hard. There's no theory, there's no intellectual process. All I'm doing is I'm just keep on adding and seeing if it's significant, I'll keep it. If it's not, I'm going to toss it away. Or backward selection, where I just throw all my variables in my data set into the model, and I keep removing them one by one and say, okay, this one's not significant, I'm going to remove it until I come with a whole bunch of variables that's significant. That really makes no sense. So again, regardless of your discipline, I mean, epidemiology is the mother and the father of all research in terms of population research measuring exposure outcomes or relationships. So I think epidemiology has quite a good say on determining how we should measure things. People in other disciplines might not agree, but that's the truth.
Yeah, so because I was even bringing that up because like last week I couple of papers that I received for review. One of these was actually BMC, and then that was part of the things I critiqued the paper for. But then the editor at some point was we understood that you are speaking from an epidemiological perspective. However, the paper is not leaning towards that end, so we would rather want to give you another, like for example, another round of review to see whether you may want to agree with the paper to be pushed out, because the paper was literally looking at the multi-level, more like structural level, to see, let's say, individual factors, household and community factors, how those helps in predicting certain childhood outcomes, like child health outcomes. But then they've not accounted for the hierarchical structure. They've not also talked about how each of those covariates are being, included in the model. All of these are important to us. But the more critical I would want it to be, the more unlikely that I accept a paper or recommend a paper for publications. So at some point, I'm like, maybe it looks like we are alone when it comes to being very meticulous as epidemiologists, in terms of how we deal with variable selections, moving around with those, little nitty-gritty stuff like that. But thank you for your input. This is helpful.
That's a good perspective, right? But the thing is also realizing that a well-trained epidemiologist is by definition a methodologist. You can't say the same force. And again, it varies by discipline, right? You have some people who are in some disciplines where maybe the only research course they took was a 2-hour course or a 2-week course on research methodology, right? It doesn't matter that they have a PhD. Maybe all the training they have in research, like formal training, is a 1-week course or a 2-week course on research methodology, right? So that does suffice. Obviously that does not give you enough training to understand what research is or how it should be conducted or how it should be interpreted. And so what people then end up doing is just repeat things they saw in the literature. So it doesn't matter at what stage they're in their career. The fact that you've been doing something for 10 years or 20 years doesn't mean it's right. It just means that you've been doing something wrong for 20 years. You're right. And so I think fundamentally the problem is the training, that not many specialties like teach you methodology of research. For most people, they just breeze through it, or they just replicate what they've seen in the past, which is definitely not ideal for evidence generation. But I agree with you that it's methodologies are trained to do that. You are trained to understand methodology and to see how issues of confounding or measurement bias or selection bias, how they play a role and how to control for those things and how to measure truth. Like you can't really say the same for many other specialties who have a need to do research but have not been formally trained in that process. So but I agree with you that it's an important issue that should be talked about more often.
Sorry, please, I just want to add to his comment. Hello?
Yes, go ahead, please.
Yeah, I just want to tell him that as a reviewer, I don't think it's to water down his valuable opinions. Because if you go on doing that, you see that what is going to reign at the end of the day is ignorance. Maybe those people were taking that stand because they know less, okay? And you know better. And if you keep on accepting, at the end of the day, you could reject that paper and then it stands rejected from your own end. Even if someone else accepts that paper is not going to be from you. And it comes to a time that, if we see people like you rejecting the reviewer on the other side, or the editors who maybe will start knowing that, 1, 2, 3 people are rejecting such opinion, maybe we'll come to a realization that something might be wrong. But when everybody accepts that, then it becomes the norm, which is going to be very, very tragic, and is not really good for the literary world. Okay, it is good that when you told us about all these assumptions, I think it is good. Though, sir, you said you were so glad that we don't really know about this forward and backward elimination things like that. I think well, it is most people will actually tell us all the assumptions that are involved, so that at the end of the day, they will tell us what is the right thing to do, which is actually what we have done. Okay, so I think this thing should be pointed out to people, and then at the end of the day, they should be told what should really be done, so that they have an informed choice. But really, going their own way, I don't think that will advance knowledge, and you should completely don't just subscribe to that. Thank you.
That's a good perspective. Thank you.
Thank you.
My hand is up, sir. Prof,
Go
thank
ahead.
you. Yes. Sorry, there's what is called choosing your variables, exposure variables or predictor variables a priori. Is that the same thing as using your intellect to choose what you can include in a model? I don't know.
A priori simply means beforehand, and that's contrasted with ad hoc or post hoc, which means after the fact. So a priori means before the fact, post hoc means after the fact. So what we're saying essentially is, and before you even sit down, and this goes back to what I was saying, first things in doing your research paper, sit down with a blank sheet of paper and say, this is the relationship I think, like this is the theory, and there has to be some theory in that. Like, how do I think the world works? Like, and then this is a priori selection, right? Where you say that this is the variables, and based on this, right, the literature supports this, and you've mapped out everything. So it's not you just doing a fishing expedition where you say, I'm just going to start running these models and seeing what comes out as significant. Like, okay, that is not a priori at all. You're just doing a fishing expedition, and that is just very subject to a lot of type 1 error, which is just results from a fishing expedition. You see results that are significant, not because they are significant in nature, but you're just looking hard, and Denzel Washington says if you hang around the barber shop long enough, you're going to get a free haircut. So you get things that are significant just because you have been so persistent in looking, and you find things that are significant. And so, yes, the basis of research is that things should be done a priori. If you're my doctoral student, I will ensure that your protocol is written up front, and your protocol is published on clinicaltrials.gov. And you cannot deviate from that protocol. Why? Because the whole point of PhD training is to make sure that we breed people who are intellect and people who can do critical thinking, not just people who just chase results, right? I am completely fine if your results... And please, Mr. Z, okay, thank you. So again, it's fine if your results don't show anything interesting. The whole point of training a scholar is methodology. It's not on it. I couldn't care less about the result, right? What is the methodology that led to those results? So that is why we should emphasize, critical thinking in especially doctoral training, that make sure that these people understand the substance and the nuance, and that is why protocols should be created by students. They should write a thorough statistical analysis plan. Those should be published on clinicaltrials.gov for the whole world to see. And once you publish that, and remember, you're doing this before you even collected your data, right? That is how it should be. And then you do your analysis per protocol. Everything is done per protocol. Not that, oh, geez, now that I've had a chance to look into the data, they don't support what I wanted to say, or I don't have p-values that are significant, so I'm going to change things. So that's essentially what we mean by a priori selection, that there's some intellectual involvement, and you have told us upfront how you think the world works, and we're going to hold your feet to the fire on that regard. Okay, is that clear?
So I think, in addition to what you said, I think this is why, these days things like clinical trials are registered ahead, because so that once you've selected your variables and all those things, even if you have negative results, okay, you just have to report based on what you have selected, because there's always a tendency for people to always do this fishing expedition at the end of the day, and I want to change things rather than sticking to the protocol. So it is very, I think in research world now, people really play a lot of value for you, going with your protocol and report the outcomes, so that we know what the truth is, rather than changing it in midstream.
Exactly, I agree, absolutely. All right. Any other concerns, questions?
Thank you, Prof. Thank you very much.
You're welcome. Okay, it seems we've reached the end of all questions. I'm looking at any other questions that we need to answer. Are we all set?
We're all set, sir.
All right, sounds good.
Bro, just
Yes.
a quick, I send my number through your LinkedIn. Probably we can have a quick discussion at your convenience. It could be over, no rush.
Okay, sure, we'll do. Thanks so much. Yeah, I'll take that.
Yeah, thank you, Prof. We're looking forward for the novice class on starter. Thank you, sir.
Will it teach the class?
No, I want to be a learner. I only know SPSS. I don't know much about starter.
You can have it in SPSS. There's no, the programming language should not matter, whether it's Theta or SPSS or whatever, right? We should be agnostic.
I think LinkedIn and Linglish should handle that, sir.
I like how you are trying to wriggle out of the situation.
Sorry, Dr. Lingley.
Together with you, right? I'll present the introduction.
I love that response. So, Dr. Hamidu, she says she's fine as long as you guys do together.
No, not me. You're welcome, sir. Thank you, sir.
Oh, that is so funny. Look called you out right away.
Because like I said, there's one question. Joshua, I think you want to speak. Am I right to say that stepwise and backward selection methods are not ideal due to its impact on interaction effects?
They're wrong for many reasons. Interaction, multiplicity is just a guesswork. It's very unscientific. It doesn't show any scholarly efforts, right? There are 1,000,001 reasons we can cite. Yeah, and all of those to be correct. So please, just completely, if you have a draft manuscript that is based on forward selection, backward selection, or whatever stepwise, just go and burn it and let's start afresh. Burn it and then grab a fresh piece of paper and start providing the intellectual input that we require. And again, this is why we award a doctor of philosophy. Philosophy means that you are someone with critical thought, right? Why are we awarding a doctor of philosophy to you? If you're not doing any philosophical, there's no philosophy in the work, right? There has to be some thinking in that process. So,
thank you, Prof. Please, I want to speak with you privately later. I'll call you, please. Thank you.
Yeah, so Prof, this is more like I'm just being critical here. Don't mind me.
Yes,
with machine learning, we get to a point where, having done the cross-validation stuff, and then you just wanted to figure out what are the predictors. Let's say this was a paper that I had to present in our machine learning seminar, here at the UF, and then it was more like trying to predict HIV factors that predict or that can help in predicting HIV, let's say positivity, seropositivity among young Ethiopian. They use demographic health survey data. And then at some point of the paper, they're more like trying to explore what are those potential predictors when it comes to HIV seropositivity among young people using a large data set. And then with that, they explore a couple of papers, a couple of factors, and you could see in the model, one of the models they presented in the machine learning, that each of the factors, for example, how much of age is contributing to the prediction, accuracy or potential, and then how much is sex, how much is education, and all of that. And then at that particular point, they don't have any a priori, approach to the method. So they literally wanted to understand generally with large language stuff. So how does that also reconcile with the notion behind this stepwise, backward, and all that, where the intention is not even having to classify exposure and then predictors with your outcome, but rather to approach a couple of data, and then you just want to use machine learning to figure out what are the predictors, and you sequence them based on their impact. What's your insight on that?
So again, I'm not against.
Prof. Hello, Prof.
Yes.
Hello, sir. I just want to chip in something to what he has said. Okay,
go ahead.
I think what we're saying here, my brother, is that for example, if you feed your model into machine learning, okay, and the outcome comes out and says something like CD4 count is not significant, okay, or the duration of HIV turned out not to be included in the model, okay, now, you as a clinician, will you rather, knowing that the duration of HIV or the stage of HIV is very critical or is important, will you rather want to include that in your model or agree with the machine? Okay, so now this is where the clinical things we are saying is important. Though it may not be statistically significant from the machine perspective, and because of that, the machine might not include it. But you as an individual will sit back and say, I'm a clinician, and I know that the stage matters here. I know that the CD4 count matters here. And most literature will rather include this. So you might not go with the machine, and you go with your clinical reasoning. So feeding model into machine, well, may give you a guide, but that is not the end of the issue. And that is what I say. And as I say, clinical reason really matter. If you are talking of malaria, okay, for instance, okay, and it comes out that seasonal variation does not really matter to machine. And for you, know that seasonal variation really matters because that is when mosquitoes thrives or something like that, or if you locations, maybe tropical rainforest versus desert, okay, or so that. So your clinical input is so critical, is so crucial, and machine will not decide that for you.
That's a very good input. Now, Amadu, let's look at it from just a basic common sense. What do you think is the number one reason why people use machine learning?
Yeah, most of the time when you have large data set and then you just want to make sense out of it.
But you can also use you can also use, we have advanced in computational power. Modern computers have a large computational power. You can use your regular, like you can do like the OLS regression, right? With that, even large data sets, right? So forget about the data now, right? Let's look at just the human component of it. Why do you think people do machine learning? Like use this kind of large, why would you think people would want to use, let's say, machine learning for that kind of research question as opposed to using, let's say, OLS regression?
Yeah, so that's a good question. So for that, you can even achieve that using OLS. You can even use other logistic framework with that question. But then most of the time, also the reason they go for machine learning, especially for high dimensional data and then these pattern identification stuff and all that. So it could be much more complicated than ordinary numbers and all. But for this research question, perfectly correct. Like, logistic can take care of it.
Yeah, so I'm just thinking, for simplicity, right? The debate is based on this particular research question. Let's forget about all the research questions. People use that model because they want to sound fancy. That's the reality, right? Like, oh wow, I just want to have this this fancy approach to here is one of my favorite journal. I'll always point out to this. Let me show you what tobacco control says about. And I think it's so well worded and so well framed that I always refer back to it all the time. So tobacco control has this piece on for authors here. And why it provides a context for what we should even really, really care about. This is, they say, the manuscript, and this is also from me coming as a journal editor, right? This is how I evaluate papers in general when deciding whether to reject or review papers. But tobacco control, I said it so eloquently that I always refer back to it. The manuscript editors will generally not give high priority to, then here are the papers here. So this is the part I want here. Reports that evoke unanimous so what response from the editors. These are papers with findings that seem to hold no obvious importance for changing policy or practice in tobacco control. Now, this is the part I want to emphasize. They often display methodological finery, but don't take us anywhere important or interesting. As a journal editor, I don't care, like the dog should wag the tail. The tail should not wag the dog. The methodology is just a means to an end, right? And so use the simplest methodology possible. Take note also that people who do machine learning are people who who have a tech background. They may know a lot about programming, right? But they have never taken one single epic course in their life, right? And so they in some cases, not all, the use of like machine learning or some of this other advanced model type is just a way of just showing off, like, wow, we use machine learning. I'm like, wow, we're so cool. We're so sophisticated. It's like, okay, but how does that take us from anywhere? Like, First of all, okay, let's leave the instrument you use. Now tell me, what is the thinking? What's the reasoning behind selection of this? And that's where you come to grind hold. There's no intellectual involvement. It's like, oh, let us just use this methodology because it sounds cool, right? We sound fancy. So I think it's always the thing about chasing the newest trend, chasing the newest, and that's one of the things that, especially as a data scientist, you want to guard against, chasing fads, right? Sure, if there's need for us to use machine learning, if we have multidimensional data, let us definitely use it. But if it's something that can be achieved with OLS regression, there's absolutely no need to just use some super complicated method just because we want to sound fancy or sound sophisticated. Because in that case, you have no thinking there's no intellectual input in most cases. You're just throwing all things into the model and trying to figure out what works, right? And again, this is why in the pharmaceutical industry, we're very careful about using this kind of methods to detect signals. Imagine how dangerous it would be if let's say you are working in the pharmaceutical space and you were talking about detection of signals, safety signals. This is a life and death issue. And you were saying, we're just going to throw all the data we've gathered around the world into a machine and let it just tell us which safety signals exist. That is extremely dangerous. You come up with signals that just make no sense, right? But are significant from the purely statistical perspective, but have no inherent meaning whatsoever, right? And that is extremely dangerous because you are now making spurious implications that have real world implications, death and life, right? And that's why we cannot use that kind of approaches in certain areas where it is extremely sensitive, because no machine can replace human judgment and that sense of intellectual input. So my response was long-winded, but also say that where it is indicated, let us use it. But where it's not indicated, human thinking cannot be replaced by machines. And so there should be, again, my point is that there has to be a deliberate, intentional human involvement. There has to be an intellectual input in the process of model building.
Yeah, and then this is perfectly inspirational, Prof. Like even when in the paper, even though they use like 8 different algorithms, in the lights of logic boosting, random forest, naive Bayes, and all this stuff, and then supervised vector machine, guess what happened? The logistic regression has the highest across all the major performance indicators like specificities, sensitivities, precisions, accuracies, and all. So that come back to exactly where the question is. It would have been better even if they only used logistic, because it still stand out to be the best across the 7 other algorithms that they use in the paper. So I 100% agree with you.
Yeah. And I think as you also grow older in your career, you care less about sounding sophisticated. You just want to convey a simple message, right? And so I think that sometimes that's one thing that is missing from the picture. Communication, right? The ease of communication, and for me, I'm a huge believer in communication. Let us communicate simple. Let's not use big words. Use small words where you can. Unless now, in some cases, you have no choice but use a big word. But that should be an exception rather than the norm, where you're speaking about people's head. That doesn't help anybody. The same thing with methodology. Robustness of research or rigor in research doesn't mean that you're using complex methodology. It simply means, have you considered threats to internal validity and external validity? Have you considered, generalizability and as relevant, right? So I definitely agree with you that we need to do better and just focus more on communication to our external audiences. All right. Any other questions or comments?
Yeah, Doctor, thank you very much for that wonderful session. And discussion is a really good part of this class. I enjoyed you and Baro and other taking. I think what you mentioned about simplicity, this is the best approach. For us in the epidemiology, what matters much more is how you get the methodology. So we are trained to become methodologists and then to apply that in appraising results. So the machine learning really is just the fancy part or trends like you mentioned, and it doesn't do much in what we do. The simplest form of analysis is always the best. And you can even see that in the bigger papers, the English, the methods, they're just simple as ABC.
Exactly.
Thank you very much.
Yeah, definitely. I can't emphasize communication enough. Let's communicate simple terms, like, you know, and that's why CDC's premier journal, the MMWR, will not accept. If you look at an MMWR, for example, this is CDC's topmost. CDC is one of the leading health agencies in the world. But if you look at what MMWR, what is published in MMWR, simple stuff with, like, please don't come and complicate our life for us, right? If you look at the grammar, simple language, because again, at the end of the day, it's the simple things that move policy, that change things. Is because who has the responsibility of making change in society? It's lawmakers, it's practitioners. These are people who understand simple stuff. Like, so if the goal is not to preach to the choir, you're not just communicating with your fellow tech researchers or high-end sophisticated researchers. It's to move policy, to move change, to affect, move the needle on things that are important. So look, I think a good practice in communication is just looking at MMWR reports. Simple, always, like no complicated language. In fact, MMWR says if you must use regression, use it. But otherwise, please don't. Just keep it simple, right? And so if you look at a typical MMWR, it's just, you see, they even have simple infographics so that everybody understands, and so the analysis are just simple. So I think that's a good trend for everybody to follow, because it's, at the end of the day, we got to communicate.
So can we get the link to that, what you're showing, sir?
Yeah, just sure, we can drop the link here in the
yeah, okay, thank you.
Welcome, yeah. Let me drop that here. Okay, one last question. Any from anybody, or forever hold your peace? Okay, no question then. All right, thanks. Lungi, any final words? And again, one of the issues we also have to understand is that it is impossible to have a session that everybody will understand 100%. So I also have to mention that, because the expectation that someone will have a session that everyone will understand equally it's a myth. It cannot occur, because we are very different levels of understanding, and this is quite a mixed audience. So even if we were to have a session for newbies, there will still be confusion. So that you have to do some work yourself too, right? You have to go and figure out some of those things and read. If you are speaking on a level that you understand 100% of the things, then you're not even challenged. You're not even learning. You got to go back and say, okay, I was confused here and I was confused there, so I have to read up. So if you understand everything we said, then that means you're not learning. You shouldn't even be here then. So that's just to address the previous point, that there has to be some pain, right? Acyclic says, he who learns must suffer. You got to suffer a little, like by spending time and trying to understand all of those things from the basics. All right, I'm tired of talking. Any last questions?
Hello?
Yes, Moses.
My not question as such, but just to ask for some recommendations, and maybe later you can advise if I can come to your inbox. I intend to pursue a Masters of Science in Epidemiology, and looking for an option, either blended or purely long distance, like virtual would be a good thing. So if you have maybe some options, I believe maybe there could be other colleagues that have that kind of thinking, but just to seek for your guidance and some options. Thank you.
Any school is fine. I don't have any recommendations for school. Any school is fine. No school is going to teach you anything useful, actually. You have to teach yourself, right? So in any school you go, you still have to put in the effort. So I mean, I don't think there's a face value to say, no, this school or that school, because at the end of the day, your effort will count more towards your learning. The degree you're getting is just a poster for people to believe you that you know something. You got to go to YouTube and learn so you know the stuff actually. So for that reason, I don't typically recommend schools or anything, because it doesn't really matter. So that's my take on that.
Yeah, it's still not bad to welcome her to the Ghetto Nation. So come around to UF, University of Florida.
That is, you're shamelessly advertising your school.
All right, at least she'll be in my department.
Okay.